All right, great. Go ahead and get running, get started. Hopefully you're here for the right talk. This is going to be on Postgres, kind of like a how to diagnose performance as an application developer so that you don't have to be a DBA essentially. Really quickly, some shameless plugs first. If you like Postgres at all, subscribe to Postgres Weekly. It's a weekly newsletter I curate. I've blogged a good bit about Postgres on my blog. There's Postgres Guide, and then I work at Citus Data that turns Postgres into a distributed scale-out database. Does anyone here not use Postgres? Anyone brave enough to show a hand? OK, cool. So this is why you you don't? You don't use it now? OK, so here's why you should. This is like Postgres in a nutshell. A ton of good stuff. If you're not familiar with something on this slide, it's worth looking it up, checking it out. Like transactional DDL, super important so that when you're running a migration and something breaks, you can roll it back. Listen notify is like pub sub inside your database. Window functions are great for analytics. Extensions, there's a ton of them. So like full text search, geospatial, a lot of great stuff. So if you ever need to convince someone why, there's a laundry list of things. This is actually a colleague on summing this up a little bit better. It's less and less of a relational database and more like a platform, although I'm a VI user myself. So to kind of separate a bit in this talk, there's two kind of workloads, OLTP and OLAP. OLTP is more like single record, kind of like write, read, that sort of thing. OLAP, you've got BI, reporting, analytics, that sort of thing. For this talk, I'm only going to cover the OLTP. OLAP is a whole other world. You optimize hardware. You get to talking about massively parallel processing and other things. So for this sake, it's basically web applications. I'm not going to drill too much into the setup or config. There, if you're setting it up, the easiest thing to do if you're on Amazon, use Amazon RDS, Heroku, Citus, or Christoph Pettis has a good talk from past PyCons of here's the 20 config things you need to do. The talk is PostgreSQL when it's not your day job. Pretty good to get set up. If you're on any other clouds, again, his talk, it says, hey, if you've got real hardware or this cloud, use all these configs, set them up once, you never have to think about them. And if you're on real hardware, there's a good book. It's about 4 years old now, but really good about tuning for real hardware. Bare Metal by Greg Smith. High performance PostgreSQL that really gets down to tuning bare metal. So worthwhile if you're on that. So at a high level, there's essentially one thing you can pay attention to from the 30,000 foot view, and it's the cache. Postgres, this isn't Memcache or Redis. Postgres is going to be really good about keeping frequently accessed data in memory. It's going to be smarter than you are about this. Trust Postgres. The best thing you can do is give your database a lot of memory. You can use this super simple query to figure out your cache hit ratio. Fortunately, you can just save this and run it. It gives you back something like this. So you get something a little bit better, more intuitive. Here, what you typically want to see is something 99% or higher. Index hit rate is the other one. And I'll drill a little bit more down into indexes in a minute. But essentially here, what you want to see is that you have indexes on big tables and they're frequently being used. So again, here you're querying a bunch of the catalog tables in Postgres. You don't have to worry too much about what these things mean. It takes care of how many blocks are dirtied underneath the covers, how many times does it use an index scan, a sequential scan. The important part is that you can kind of understand this query that comes out of it. And what this is going to show me, I don't know if you can see that really well, it's going to show your table name, it's going to show the percentage of time your index was used, and then it's going to show how many rows are in the table. And as an application developer, I would say here are your rough guidelines. Cache hit ratio, you want to be at 99%. Run this regularly, that query regularly against your database. If it drops below that, it's not like queries are going to start going from 1 millisecond to 2. They're going to go from 1 millisecond to 150 milliseconds. So as soon as you drop below that 99%, you're going to start to fall off a cliff. For index hit rate, it depends a bit on the workload. This varies a little bit. Sometimes, you're scanning a bunch of rows and it won't use the index, but generally you want to see something above 95%. And I say where you have rows of greater than 10,000. If you've got 100 rows in your database, it doesn't matter. So this is really kind of for a production load database. So shortcuts. I showed those two queries. How many of you have a bash RC file? Or a vimrc or something like that? How many of you have a psql RC file? A few hands, awesome. So psql RC, you can kind of have like all sorts of customizations in here. \x auto is great because it'll automatically format the output of a query to size to your screen. But if you notice down here at the bottom, I have this set show slow queries. I can put the cache hit ratio query in here and then just run select show slow queries, and it'll automatically run this query for me. So I don't have to remember it. All these frequently used queries I can put directly into this file and just run them by name. Super handy. So great. At a 30,000 foot view, make sure you have the right indexes and that you have a good cache hit ratio. But how does that help with like specific, let's drill in a little bit to like a specific query. So this is a pretty straightforward query. If you know SQL, give me the last name of employees who are making more than 50,000 a year. If you put explain in front of this, Postgres is going to tell you basically the query plan it's going to execute and some estimation around it. So you see down here at the bottom, you see this kind of unintelligible stuff. If I go back here, like it's super unintuitive, even to someone that's been working with Postgres for nearly 10 years now. The startup time you can mostly ignore a bit there. The other kind of that max time and rows returned are two things to pay attention to. Now on an explain plan, this is going to give you the estimates. If you run explain analyze, it's going to actually execute that query and tell you its estimates and how long it actually took. So there, what I'm going to get back is, again, the startup time, which is pretty small. That's in milliseconds. The max time, which again is in milliseconds. And the number of rows returned. Down there, you're going to see the actual time as well. And this is kind of a key thing to pay attention to if like, OK, there's this query I'm running. Is it slow or not? So that'll give you the time back as well. Drilling in, I would say here's what you should expect on most web applications. Like a page response time of under 100 milliseconds is pretty good. Common queries should execute in under 10 milliseconds. I actually usually target about 1 millisecond. That's pretty reasonable to get down to. And then rare queries, less than 100 milliseconds. Here, if you're doing like give me a list of users or that kind of thing, if you've got a reporting screen, the Django admin screen, those sort of things, expect them to take a little bit longer. So we can come back here and see that we've got this query, took 295 milliseconds. So that's all in milliseconds. And that's, as we can see, bad. So here what I'm going to do is I'm querying last name for salary. I'm going to come in here and add an index on salary, pretty straightforward. And we can see that now this is going to run in 1.7 milliseconds. The difference there, it's going to now use an index scan. So it's going to basically use the index, know exactly where to go for that record. It's already in memory as well, much, much faster. So this is great if you say, hey, there's this one query, I know it's slow, how do I fix it? But for a lot of applications, you have kind of no idea, where are my slow queries at? You build a Django app, and you've got hundreds of queries running. How do you have any idea? Enter pgstat statements. This is an extension to Postgres. It ships with the contrib. You should turn it on by default no matter what. So as soon as you install Postgres, run creates extension pgstat statements. If you're on Heroku, this is already enabled. RDS, I'm not sure if it's already enabled by default, but if not, you should automatically enable it. What pgstat statements does is record every time a query is run and essentially normalize it. So you see where like I have select star from users where email is question mark there. There was actually a value in there. And every time I have a value in there, it's going to replace that as if it's parameterized. It's going to record all these other things about like how many shared buffer blocks were dirty, how many were written, all these things under the covers which are useful. You don't have to worry about them too much. From this, we can run a pretty similar query to how we looked at our cache hit ratio, our index hit ratio. This is going to give us this result, which is going to say this query has taken this total amount of time on my database, and this is the average amount of time for it. If you run one row lookup constantly, that'll be the most expensive query in aggregate, but it may be OK on an individual basis. Here I can do a little bit of math and say, OK, I've got the first one, 10 milliseconds is kind of at where I wanted it to be. I've got the second one down there, though, that's at 80 milliseconds. That's much closer to that 100 milliseconds I don't want to be at. I can come in and optimize this and get a lot of time back overall in my database. So this will give you like a nice view of like, OK, where are my bad queries at? What do I need to optimize? Indexes. Postgres has a lot of indexes. I'm actually missing one. There's a new one now as well. So there is btree, gen, gist, knn, spgist, and there's a new one also coming called vodka, because there's a small detour. There's this group of kind of developers in the Postgres community known as the Russians. They are all over there in Russia. And they come up with a crazy idea for a new index every year. They show up on the mailing list, say, here's this proposal. Everyone's like, it's crazy, whatever. It's not going to work. It doesn't make any sense. They go into a hole for 6 months. They come out later, and it's like, here it is, and it works perfectly, and here's the performance benchmarks. And it just ends up getting committed to Postgres. So I think, yes, 4 out of the 5 of these are all from them. And because they're Russian, they said, we have gin, and we need vodka. True story. But if you're like me, you read through this, even in the docs, and it's super confusing. It's like, if you have this exact case, and here's how it works, this is what it's for. Slightly oversimplified. This isn't 100% of the case, but roughly, like, this is what you want. And if you're really optimizing Postgres, you can drill in further. But btree, 99% of the time, this is what you want. When you want to index on a single column or a couple of columns, this is kind of what you learn in CS school, a standard btree index. Gen index. It's generalized inverted index. The way to think about this is if you have multiple values in the same column. So if you have like an array data type, which is an awesome data type in Postgres, feel free to use it. There's HStore, which is key value store inside Postgres. There's JSON. So basically, if you've got multiple values inside the column, it's going to index every single one of those values. Gist. If you have, the way to think about this is if you have values that overlap. So text search. So if you've got kind of parts of speech that you want, like this part of the sentence might overlap with this one, that sort of thing. Or if you've got shapes. So if you're doing geospatial stuff, if you've got polygons that would intersect. If you're doing anything with those in your database, a gist is usually what you want. In some cases, gen and gist can get swapped based on how performant they are, or space on disk, or that sort of thing. But that's a rough rule of thumb. For knn, it's for similarity. spgist, and I say this every single time I've talked about this, I ask what it's for, and I get back an answer from every kind of Postgres community person, and the only thing I know is phone numbers. Beyond that, I don't know. But basically, if you have very large amounts of kind of like things that naturally group together, I guess because of the area code and kind of prefixes and that sort of thing, use spgist, or if you have phone numbers and you need to index them. So a few more on indexes. So there's all those index types, but there's also conditional and functional indexes. So a conditional index is like where something is true. Let's say you have you're a phone book, and you have everyone's historical address, but you only want to index their current address. Not many people search for the old one, so maybe you just have a Boolean field of saying address is current. In that case, you might want to index only that, and that's going to be like 1/10th of your data. In that case, it's going to be much faster. You're going to index less, use up less storage. So there, you would just say, create an index, and then put that where condition right on the index. Functional. Functional indexes, if you wanted to say, I've got this JSON data and I'm calling this function to grab me the numeric value of the population for some reason, or whatever function. You could be the lowercase value of a text if you always search on the lowercase, right? You basically just, same thing. If this is what your query normally looks like, and if you're using something like the Django debug toolbar, and you see the query there and there's a function around it, you actually want to have that on the index. You don't want to have the index without it. So here again, I'm going to index probably like you'd expect. Create the index on whatever field, but use the function directly in there. Another thing, create index concurrently. So when you create an index, it's going to lock the table. If you create index concurrently, it's going to do all this work in the background, slowly build up the index, and then as soon as it's live, it's going to cut over to it. It's about 2 to 3x slower, but basically, it's if you've ever come over from MySQL where like doing anything kind of causes your database to go down, an index kind of has that that cost. Create index concurrently basically frees you from that. HStore, JSON, and JSON Be. HStore used to be one of my favorite data types in Postgres. It was a key value store directly inside Postgres. So you've got like NoSQL inside of SQL. Then came along JSON, and everyone got really excited about it. But it was basically just a text field that did JSON validation. There was nothing special about it. And then we got JSON Be. As a coworker likes to say, the B is for better. It's actually for binary, but I prefer his definition of it. If you're really curious, there are cases where you might want JSON instead of JSON Be, or HStore instead of JSON Be. For the most part, if you're doing anything with kind of like no schema, documents, NoSQL document storage in Postgres, JSON Be is what you want. So JSON Be, it's in Postgres as of 9.4. So if you're running with 9.4 or more recently, you can create a column and just use the JSON Be data type. From here, you can kind of get an idea. It's JSON, you can cast it, you can query it, you can put whatever you want in there. And it's nice because you can query directly into it. So I could say like, select star from users where the conference they're attending is this one. The really nice part about this, coming back to the indexes, is the gen and gist indexes work. And that means it's going to be really fast for retrieving JSON Be stuff. There's some benchmarks out there saying, hey, it's faster than Mongo this way, that way. I don't know if it is. It probably depends on your workload. But what this is going to do is index every key and value inside of that JSON document. So you don't have to worry about, like, am I querying this key or looking for that value? It's going to index everything in there for you. Pooling. This used to actually be a really bad issue in Django. It's gotten better. So when you make a request to your database, it's going to go out and get a connection. And that takes a little while if you're doing things securely with like SSL and otherwise. What's common is to have a pool of connections just sitting there when you're running your web server. Django now has persistent connections, which keep them alive, which is better. There's also a few connection poolers out there. So what you can do is use an application layer one, which is good to do. The persistent connections in Django works pretty well. If you don't have it turned on, I'd encourage you to. You could also run a standalone daemon. These are at higher scale when you've got kind of like 100 processes connecting to your database and that sort of thing. There's two big ones out there. I would say just use pgbouncer. Don't even think about pgpool. Pgpool is like a Swiss Army knife that tries to do a ton of things. Whereas pgbouncer is like more of the Unix, like one small, really sharp tool that just handles connection pooling. So we looked at some queries, or a query, and overall like how to pay attention to which ones are bad, optimize them, add indexes. But at a certain point, you're going to have to like add cache to your database. If your cache hit ratio drops, doesn't matter how much you index things, it's just going to be slow. So at that point, you basically increase the cache by spending more money on your database. What you're going to want to do is increase the memory there. A couple of options. The first is vertical scaling. This is the easiest thing to do. Like, scale up, scale up, scale up as long as you can, because it's so much easier than thinking about scaling out. When you do need to scale out, there are a couple options. You could go and look at like another distributed data store, like a Cassandra or something else. You could manually shard your data. A lot of people will do that. If you do that, please don't use schemas. There's all sorts of gotchas and caveats and issues when you go down that path. A slightly shameless plug, you could use something like Citus, which allows you to shard it out across multiple Postgres instances, or you could roll your own. But at that point, basically, you're saying, hey, I have a bunch of smaller instances, and I have more linear scale. For backups, there's two kinds of backups in Postgres. And they actually do have performance implications. So pgdump is what most people think of. That's when I get like a SQL dump, a bunch of insert statements in the data. This is what's known as a logical backup. You can take it, load it up anywhere. You can bring it down to your local development environment, pull it down to staging. It's human readable and extremely portable. There's also a physical backup. So this is using PG base backup and the wall in Postgres. So this ships with Postgres, actually both ship with Postgres. This is kind of under the covers and what a lot of people do for things like continuous backups using things like Wally. Logical backup is what most people do. They do it like every 24 hours, that sort of thing. It's good across architectures, but the downside is it introduces load on your database. It's a pretty intensive process. It works at about under 50 gigabytes. I'd say it can go up to 500 gigs, but at that point it kind of starts to fail. The solution really kind of long term is to take care of physical backups. They're a little more initial setup. You should look at using a tool like Wally, which is written in Python. It's less portable, so you have to be on the same like architecture and infrastructure, but it has much less load on the system, so it doesn't introduce load to your database. All right, I was worried I wasn't going to get through all like 65 slides, and I flew through them. So really quick recap, and then plenty of time for questions. So OLAP is a whole other talk. There you really care about like how things are clustered on disk together. Looking at doing things like MPP systems, massively parallel processing. There's a bunch of those out there like Greenplum. Citus does some of that. Redshift is in that category. So you're looking at very different systems there. If you're looking to roll your own, PG reorg is a pretty crazy extension that like reorders things live on disk for you in Postgres. Take a look at it. For web apps, like number one, ensure that your data is in cache. Like save that query, run it on a weekly basis. As soon as things like fall out of cache and you drop below 99%, performance is going to fall off a cliff. Optimize the overall query load. Don't worry about it page by page. Like you can mostly ignore it, but pay attention to pgstat statements and what are your expensive queries and what do you need to optimize. Then throw indexes at them. You don't have to worry too much about overusing indexes. It's not going to be that bad for your database. You can be pretty liberal with it. And then when cache sucks, throw more at it. Great. I went a little faster than I expected because I was worried about getting through, but plenty of time for questions.